All right, thank you all for joining after lunch, and I want to thanks to the conference organizers and apologies to the hundreds of people who have contributed to the field of exoplanet detection who I just couldn't fit into the slides. So what I'm going to try and do in this talk is present the individual techniques, the Doppler technique, what we're doing new with infrared spectroscopy, transit observations, which will be covered more by Niku Madhusudan, also adaptive optics imaging, and what's on the forefront for microlensing and astrometry. So in this nice animation by Xavier Demusque, you can, as a reminder of the Doppler technique, we're sitting here observing the spectrum of the star, which is shifting back and forth as the star orbits a common center of mass. And we map out night after night over some long, often long periods, this is only a 10-day orbit, the motion of the star as it's being tugged around this common center of mass by an unseen planet. And then we model our data, of course, to find out measure the orbital period and to derive the mass of the planet modulo the inclination of the planet, and also with some, including some uncertainty from the mass of the star itself. With each of these techniques, I'd like to give you a little glimpse into where the field started, where the field is now, and what the future looks like for the techniques. There are observational incompletenesses in each technique, and so all of the techniques fold together to build a beautiful picture, right? From each of the individual pieces. With 51 PEG, here are the data shown from the Mayor and Coulot paper in 1995, the detection of what we thought then was the first exoplanet. The precision of the day was about 10 meter per second precision. And from a technical standpoint, if you're an instrument builder, this corresponds to measuring Doppler shifts that are good to 100th of a pixel shift. So quite a feat, I think. And then once, it took a while for people to broadly accept that these Doppler measurements really were exoplanets, that they weren't just non-radial pulsations in the star or something else that we didn't understand. But once we accepted that 51 PEG was a planet, we could sort of look back and realize that in fact the field had started a bit earlier. Gamma Ceph was detected by Campbell, Walker, and Yang in 1988 as a possible planet around an evolved star, HD 114762 by Dave Latham, and then of course Alex Volchin, who found a Earth-like planetary system around a neutron star. So already the field was beginning to come into existence. Where we are right now, in this image that was put together by my co-author Greg Laughlin, shows the planet detection, and here on the y-axis you see the planet mass, and on the x-axis you see time in years, okay? And so in the beginning we detected the big massive planets. That's no surprise because they exert a large reflex velocity, and with time we get down to lower and lower mass planets. And Greg, who crosses the line between a theorist and a phenomenologist, observer, always said that, look, we can simply extrapolate, and then, by 2012 we'll find the first Earth mass planet. And he got a little lucky there, I think, because each of these improvements came about this is not just some Moore's law growth in the detection of exoplanets. This is a lot of hard work and instrument development and improvements on that front. So to keep going in this direction, we're going to need to amp up our techniques. If we make a plot, sort of a theoretical cartoon of the mass of planets and Earth masses as a function of their orbital period in days, and we imagine that at least for habitability, that rocky planets are interesting. These might be planets that are, 1 to the top level here is hard to estimate, but a few times the mass of the Earth. At distances from their host star where liquid water might pool on the surface, then we have this interlap region where the habitable worlds might exist, worlds at least like our own around other stars, and we can argue about whether that's too human-centric view, but in any case, we start looking for what we think we'll recognize. And then over time, this shows again the addition of the planets as a function of detection year. Here we are in 2000, and you'll see that, like Greg Laughlin's plot showed, we are pushing down to lower and lower mass planets. But even now in 2012, 2013, where this burning hot detection was made of a planet orbiting Alpha Centauri b, that planet is still only in a 3-day orbit. The plot is shown here, again in the paper by Demusk et al. That appeared in Nature in December of last year. The HARPS team has done remarkably well, especially on these very low amplitude systems, and I think this is because they have attacked the problem with an incredible instrument that has unprecedented stability, unlike the instruments that we've been mostly using in the US. So now the precision is down to 1 meter per second, and that means that we're measuring now pixel shifts not of 100th of a pixel, but of 1,000th of a pixel. And if the orbital period and the amplitude of the orbit is 1 meter per second, that's the amplitude, 1,000th of a pixel shift that we're watching, the lines go back and forth. So we've been attacking this technique. I've taken the speaker's prerogative of throwing in just a few slides about my own group. We're trying to take a very methodical approach. We know the problems are coupling light to the spectrograph, building an instrument that's exquisitely stable in terms of temperature and pressure, figuring out good wavelength calibration, and figuring out the noise in the stellar atmosphere, and also having the best analytical modeling techniques. So we think that we and others have solved the problem of coupling light to the spectrograph. We built a spectrograph which is now running in Chile called Chiron. You can actually get time on it through the SMARTS consortium or through NOAO. It has extremely high precision, up to 130,000. This is what a high-resolution spectrum looks like. The sodium D lines hit almost zero. They're completely opaque. And we've been able to use this instrument as a test bed for understanding what we need to do to improve our technique. So after we commissioned the instrument, this is November 2011, we looked at Tau Ceti, which is a famously stable star, and we're disappointed that although our individual error bars were less than 1 meter per second, the RMS, even over just 10 days or a couple weeks, was still 2 meters per second. We decided that's not good enough, and we sat down and brainstormed about how to improve things. We retrofitted the instrument by putting a new shell grating and a vacuum enclosure, adding an exposure meter, better temperature control to the instrument, an octagonal fiber to inject the light in, and now we're getting on that same star, Tau Ceti, over something like 10 or 12 days, internal error bars that are better than 0.5 meter per second and an RMS of about 0.5 meter per second. I think the issue has never been iodine versus thorium-argon cross-correlation techniques, but there was another reason to get rid of the iodine, which I'll tell you about in a moment. This instrument, by the way, was built with $600,000 of stimulus funding money, so we could never build an instrument like HARPS is that's that well engineered. So to get to the next level, to get to 10 centimeter per second precision, where I truly do believe that we can go, we need all those things that I told you about. The better engineering, coupling of light, wavelength calibration, the right stars, and we have to be able to finally solve for the floor of the stellar noise. So there are some people who have famously said, we've already hit the floor of the stellar noise. There's no point in trying to go after Earth. You won't do it. Stop wasting money and time and so forth. The problem with that opinion is that you're right. If we keep using the instruments that we have right now, we won't get down to 10 centimeter per second precision. But if we instead build instruments that can also find the very subtle effects of that stellar noise imprints on the spectrum, the line profile variations, the tiny temperature changes. These have a color dependence and an imprint that's different, unique from the Doppler shift, but we haven't had the resolution and the sampling that we need to find it yet. That's what, of course, the future holds. So in the next few years, you're going to see Espresso go on the VLT. We're also trying to design an instrument that will incorporate all the things we know, and the target precision will be 10 centimeters a second, where now we're trying to measure Doppler pixel shifts of a 10,000th of a pixel. And those could be amplitudes as well. So that is quite an impressive feat, a difficult thing. The bias in the optical Doppler measurements is that we look mostly at late F, the G, and the K dwarfs, and the early M dwarfs as well. The late M dwarfs simply don't have as much flux in the optical part of the spectrum, and so there's ongoing effort to build spectrographs that could be especially well suited for observing the mid to late M dwarf stars. These instruments include the Habitable Zone Planet Finder, HPF. Suvrith Mahadevan, co-author, is working the lead on that. And Carmenis, of course, Andreas Kirnbach, who I saw, is leading that effort with a double-arm spectrograph to look at the infrared and the optical. So these will finally give us access to the stars that are the most populous in our galaxy, the stars that make up 70% of the stars in the Milky Way galaxy. Suvrith Mahadevan wanted me to tell you that, this is serendipitously, this infrared detection of planets has already begun, and one example is HD 114762 with apogee, where you can see, and it's kind of fun because there's a parallel that it's HD 114762, which was Latham's planet from 1989, was unexpectedly, they weren't going after it, but they detected the planet around that star as well. So it's already beginning. It's the first, one of the first, near IR RV planet detections. They are incorporating new technology, things like laser frequency combs and stabilized etalons, to try and improve their precision and to get good wavelength calibrators for the infrared. And the on-star results with the Pathfinder instrument from the HPF showed something like a 7 to 15 minute radial velocity precision, but it's over relatively short term. So we'll have to they'll have to keep pressing on that, improving the precision and making sure that the systematics are taken care of. And the future there, as I said before, are things like HPF and Carmenis, the new instruments on the horizon. The next technique that has been so incredibly productive is the transit technique. And here you see a cartoon showing what happens, the light curve that we get as a planet transits its host star. Starting in the beginning, where the field started, was with HD 209458. And you can see there the precision, right? Watching how the precision improves with time is one of the most interesting things to me. So this goes back to the year 2000. And here's some data from 2008 taken with the very productive HAT network, the detection of HAT P7, I believe. And you can see the model light curve here to the data with quite a bit of shot noise around that light curve. And then, of course, along came Kepler, observed the same system, only now the data points are beads on a string with this amazing instrument, Kepler and Corot, that have really changed the field. This plot from Natalie Batalla shows the planet candidates from Kepler, an incredible number. If you still look down here at sort of the Earth-sized planets at Earth-like distances, there are very few that qualify, and they're very far away. They're orbiting stars that are very far away. It's great science, don't get me wrong. It's one part of the problem. So the number of what Kepler set out to do originally was to figure out eta sub Earth. And the great quote from Bill Barucki now is that practically all sun-like stars have planets, and something like half of them have planets that are between 1 and 4 times. I think this should be the radius of the Earth. Maybe mass of the Earth is a fair statement as well. And there are so many multiple planet systems. So, we now have a view of planet formation and evolution that's completely different than what we had before 1995 and even through the early 2000s. It's astonishing. There are independent analyses now of the completeness statistics for Kepler, and you can see that in this paper by Pettigura, Marcy, and Howard, that they are finding, the most abundant planets are the smallest planets, and then a dramatic drop-off with the size of planets. So it tells us that the formation of these small planets is a very robust process. I'm going to actually leave this slide that Greg Laughlin provided to Niku Madhusudan to explain, but we're getting incredible information from the combination of radial velocities and the transit technique. It gives us the mass and the size, and therefore the mean density of the planet. It's been a stunning amount of information. And then what's on the horizon in the next few years for the transit technique is TESS. We're looking forward to having this all-sky survey of bright stars for transiting planets. Okay, the next technique in my whirlwind tour of detection techniques is adaptive optics. And this is a field that has absolutely grown right underneath of all of our eyes. It's really quite stunning. So where the field started was with conventional AO systems, which try to concentrate the light so that the amount of light that's captured, the Strel ratio, is high, right, in a very small area. The problem is that there's always wings from the PSF that spread out. And at least until now, in this image, the yellow shows the star and this little blue blip is a planet. It's not hard to understand that most planets would be lost in the Strel ratios of the AO systems of the early 2000s. But what the AO imaging does is, of course, suppress the light from the star in a way that you get down, suppress the halo, I should say, of the star, so that you can begin to image planets around the star fairly close in. There are lots of clever techniques. I think the field started with ADI and LOCI, PSF modeling techniques. Moreau et al. Did a lot of the pioneering work on this, where you take several snapshots, AO snapshots, you combine the images, so that you begin to average out the noise. And you finally, with this technique, by co-adding frames, get down to suppress a lot of the wings of the PSF and begin to detect planets like this in this image of HR 8799, where you can pretty clearly see the planet. Here's another slide showing same system. And the point is that at least for the young stars, these stars with young planets that are more luminous are reachable with current adaptive optics techniques. They have a contrast ratio that's something like 10 to the -5 relative to the star. And so it means that we can find young Jupiters that are hot, but we still can't find the cold Jupiters with the traditional techniques. So what the field, now once you finally see, though, the image of the planet separated out, you can begin to study the planet's atmospheres. And here's a spectrum of HR 8799c, where carbon monoxide and H2O absorption were found. In the next few years, in fact, in the next few months, GPI will be commissioned around Gemini South. And the hope there is to go from images that look like this with the best current Keck AO corrections to images that look like this. So we'll gain not just a factor of 2, but a factor of 100 in the precision and in the contrast ratios. And that will finally give us access to Jupiters that are further out with these extreme AO systems. To get to the really cold Jupiters, a mission like WFIRST is probably going to be needed. Hopefully we'll have a 2.4 meter telescope or two that can be commissioned for this kind of a search, and it would be provide a stunning yield of planets that are at wide separations. So the next technique is the microlensing technique, and I think we all, if we took a vote, have to agree that microlensing is just absolutely cool, that the way the physics of gravity works, that the bending of light around the planets, to be able to detect the microlensing events is really an amazing process, an amazing technique. Where the field started was, of course, searches for dark matter. So you see these light curves brightening that occurs as the lensing object travels in front of the source object from our point of view. And one of the great things about this technique is that it gives us access to planets that are at larger distances, at larger semi-major axes. And also, it's not as sensitive as the other techniques, like the Doppler technique in particular, are to the planet mass. The key thing is the geometry. If the system is very well aligned, the amplification can be a factor of 100, a factor of 1,000 even. So incredible signals that can come. And here's a simulation by Scott Gowdy, which shows what's happening. They like to actually have the source star moving rather than the lensing star. But as the lensing star passes in front of the source star, you get a brightening. That amplification is from the star. But if the star has a planet, then you get a second peak. So again, it's the near perfect alignments that give you these incredible amplifications of the light. By the time the lens object is 1 Einstein radius away, if it's a planet, then the amplification becomes much smaller, much harder to detect. So it's all about alignment, I think, for this technique. So one great thing is that the width of the microlensing event tells you what type of planet it is, what the mass of the planet is. For Jupiter-like planets, these tend to be day-long brightening events. For Earth, it's only hours long. But in any case, we're on a planet that's rotating around its axes, and so you need to have good longitudinal coverage of these events. You have to track them through time. And so that can be the tricky thing, bias for this particular technique. Microlensing has found not just single planets, but also multiple planet systems, and has the ability uniquely to detect planets that are not even bound to stars. So it gives an incredible amount of information. And I think microlensing in the next few years, the exciting stuff will be microlensing from space, because getting above the Earth's atmosphere is really important for the photometry with that technique and for the time coverage. So we're hoping that the W1 mission will go forward and detect these planets. The next technique is astrometry. This of course, has laid the foundation of astronomy. It tells us what distances are to stars. We can measure by measuring their parallaxes. It tells us what their proper motions are. It tells us about binary star orbits. And in principle, it maps out the full three-dimensional orbit of a planet that's going around a star. The challenge has been that the astrometric amplitude tends to be milli or micro arc seconds on the y-axis here. Johannes Salman has made up this plot for our chapter as a function of time. So the challenge is the astrometric motion is incredibly tiny. We're still looking at the star, and we still have to observe for one full orbital period, like the Doppler technique. So the ground-based astrometry it's been definitely challenging, and I think the exciting developments here will be to go above the Earth's atmosphere. So the launch of SIM would have been fantastic, but we're really looking forward to the launch of Gaia. Gaia is going to monitor 1,000 million stars. It's going to visit each star field something like 70 times over a 5-year period. It'll have extraordinary precision, tens of micro arc seconds precision. It'll still need to map out a full orbit, so if it's a 5-year lifetime, they'll get out to something like 5-year periods, and I'm sure there will be people who are in the audience who will say, but sometimes we can get a little bit longer. I agree, but just as a benchmark. Okay, so then finally, to present my conclusions, I want to emphasize the fact that we haven't really detected rocky habitable worlds yet, and that's what we were setting out to do in the beginning. We wanted to find planets where there might be life that we can recognize. There's still the exoplanet statistics that we have now look extremely promising. We know that almost every star has planets. For people who are coming in to the field recently, you might think, of course, that's what we thought in the 1990s because of Star Trek. But it wasn't until they were actually found, and we went through this rather painful process of detecting more and more of them that we have this information. information. And we know that small planets similar to Earth are extremely common, the most common, much more common than the gas giant planets that were first detected. Okay, my third conclusion, my first one is it's not mission accomplished yet. So for the protostars people who wish the exoplanet people would just go away, we still have work to do. But then finally, the detection techniques, all of them are going to make vigorous advances. Every one of these techniques is real. People are pushing the envelope. We're going to have higher precision radial velocity surveys, both in the optical and in the infrared. There will be new all-sky transit surveys where new high-contrast AO systems are coming online and are planned for the future. There'll be hopefully space-based microlensing missions like WFIRST that could double the number of known planets and find the planets that are in wide orbits, something that we're not sensitive to so much with the other techniques except for direct imaging. And then of large planets, and then space-based astrometry, Gaia in particular, which will be sensitive to very wide orbits, but we'll need to follow them for the complete orbit. So we still have a lot of work to do, and it promises to be a very dynamic future for exoplanet detection. Thank you.
Thank you, Debra, for this very nice overview of detection techniques. So we have plenty of time for questions, actually. So let's start here from the center.
Hello, I'm Katja Poppenhager from the CFA. Hi.
Hi.
So there is a lot of effort going on at the moment to detect planets around low-mass stars.
Yep.
And especially for the low-mass stars and for the Doppler technique, there's a question of magnetic activity of the host star. So where do you see the bigger challenge for the years to come? On the side of instrumentation, getting higher resolution, higher signal to noise, or on the side of actually understanding the signal we get properly, and especially in terms of the magnetic activity?
Yeah, that's a great question. So I think that the first part, building the instruments, we have a pathway forward, but without continuing along that path, we'll never get to the point where we can do the important and difficult thing of finding the stellar noise. But it's going to be there. There will be, Zeeman splitting. Again, it means incredible oversampling, not just Nyquist sampling, I think, of the PSF, but something like, 3, maybe 4 times Nyquist sampling. So if you're looking at line bisectors, you have an exquisitely sampled line, high resolution, maybe 150,000. Yes, I know that way oversamples the line, but it doesn't way oversample the noise sources. So I think Espresso is going to be that instrument. I think we're moving on the path to trying to build that instrument as well. But the big challenge is just what you said, figuring out the stellar noise and then decorrelating it.
Left.
Laurent Pagani, Observatoire de Paris. Have people detected microlensing events with Kepler? If not, why? And how will WFIRST improve on Kepler for that?
Yeah, great question. So I actually have an undergrad who's working this summer to try and detect microlensing events in the Kepler data. There's one paper, it's by Phil Muirhead and colleagues, where they detect a it's not a microlensing event per se, it's just that the transit depth from a white dwarf companion was filled in because of some amplification from essentially microlensing. But, a big question is, where are all of we know that the black holes have to, in our model, have to be formed as stellar remnants. So, where are all of the stellar mass black holes, and why haven't we seen more of them? I think if they're in the Kepler data, it's been, the Kepler mission was focused to finding transits. You could do a parity switch and look for the lensing events as well, and so that's what I'm sure my student and I'm sure others are also doing. So it could still be buried in the data. There could be, the estimates are anywhere from tens to 1,000 of them. I think 1,000 is on the high side, and yeah.
Is that right?
Hello, Planet? Yes, hi.
Yes.
This is Gabriel Mahler from MPIA. I'd just like to make a comment about direct imaging, just to add a bit to what you said. So with this technique, actually, since you measure the luminosity of the planet, you can get information about its initial conditions, its initial luminosity. And what's traditionally done is to use hot start cooling tracks to interpret these direct detections. It's fine if it's an old system, but if it's not, which is usually the case in direct detections, you still have the effect of the unknown initial conditions, whether core accretion or gravitational stability. there's a whole range of initial possible luminosity. So when you interpret luminosity or a magnitude, you need to consider the whole range and not just consider the hot start. So that turns out to give you actually just a lower mass, a lower limit on the mass of the planet, because if the object is colder, you need to increase the mass to compensate. And so this is interesting in its own. You need to take this into account to get these statistics right. And also this procedure gives you a minimum, a lower bound on the initial entropy, the initial luminosity of the planet, which then you could try to compare from results of population synthesis. And maybe it turns out that you can't say anything because you have a whole range, or maybe you can say, well, most objects are core accretion or cold start or whatever. So I have a post on this to advertise K14,
Yep.
come see me, and a paper, but I think this is an important point.
Thank you so much, yeah.
Okay. Here in the center.
Hi, this is Feng Tian from Beijing, China. I have 3 short questions. First, what are your comments about a recently found potentially habitable planet in the GJ667c system? Second, you mentioned that you need one complete orbit for that space-based astrometry.
Wait, I'm sorry, can my memory is just, could I just answer one question?
Please.
Because you have them written down.
If you allow.
Okay,
We have plenty of time.
so Gliese 667c, I'm trying to remember, I know the first author on this, I'm blanking. It's Tuomi and colleagues, and they analyzed the HARPS data and found another planet. So I think this is an incredibly important effort to try and figure out with whatever statistical analysis techniques one can use to figure out whether there are extra signals in the system. I think I would like to see some sort of a threshold set on statistical significance, because I remember I had a team analyzing data, synthetic data from JPL that included simulated sim data plus radial velocity data, and it was quite easy to be confident that there was a signal there, which was below the sort of threshold that JPL set, and I now understand why. So the question is, it will still take more data, I think, to follow up and confirm those, but it's the right path of pushing the field.
So you are not convinced it's there? That's my simple understanding, right?
I think I said what,
You said a more diplomatic way, but that's good.
I
So
don't-
the second quick question is, you said you need one complete orbit for the space-based astrometry to confirm. What about half an orbit?
Yeah,
What
I
about
knew
a
somebody
quarter?
was going to say that. Okay, so it depends on the phase. If you happen to catch, going sort of over the 2 peaks, then you can extrapolate. But then what you've missed, which I've learned with the Doppler technique, is the multiple planets that are embedded in there that screwed everything up. So, what Scargill and Black and Scargill said in 1986 is that you had to have 2 full orbits, and in their simulations. So.
May I ask one more trick?
What
about the 3D information? You said potentially you can get a 3D information from
Yeah.
space-based astrometry.
Yeah,
Are you sure?
extremely exciting and important. Yep. Right, thanks.
Koro.
Yes. Günther Wuchterl, Koro at Tautenburg. Debra, I will wonder forever which instruments you used to select your planets that you talked about. Was it a grating or was it a prisma? But to be more serious,
Okay.
it's a great challenge. The density diagram you showed,
The which diagram?
Laughlin's density plot,
Oh, yeah.
which I think is a key progress
Yeah.
of the last decade.
Yeah,
Absolutely.
absolutely, I agree.
I think you should say that half of this comes from the Koro mission. It's half from Kepler, half from Koro.
You're right. No,
I think there is enough time to say that.
there is enough time, and I have to apologize for that lapse. I actually, never mind. I thought of that and just should have stuck it in. But absolutely, there's exciting results from Koro as well. Yeah. Sorry for being so US-centric. Yeah.
Gilles.
Gilles Chaboyer, out of job in astronomy since this morning. Just a point I didn't have time to mention in my talk, and I'd like to come back in your talk, about the microlensing. Microlensing is a very useful technique by all means, but the point I want to make, as we discussed with my friends a couple of days ago, is that when you observe a planet orbiting a lens star, the chances that you get the right results are fairly reasonable, because you're already in alert, and you have the caustic superposed to the lens stars. Now, for an unbound planet, call it the way we want, a free-floating planet, you're not in alert, right?
Yes.
So the chances that you get a spurious effect are extremely large.
Yeah, very good point. Okay, and bears on the detection, I guess, the announcement of a year ago or so, yeah. Yeah, all right.
Thank you.
Heike Rauer from DLR Germany. Just for information, I want to point out that what we feel is the next thing to do is not only to detect the planets on wide orbits, but also to get the densities and characterization, as we heard in the talks before the lunch break.
Right.
So from the European side, we are trying to follow up the Kepler and TESS surveys with a mission called Plato to detect the small planets and get their densities. Because I think with Gaia, you do get planets on the wide orbits, but you will not address the terrestrial-sized planets.
That's right. I agree completely. Yeah. So and there's also CHEOPS or CHEOPS, and there are other missions as well. Yeah. So I agree. Important for characterizing the detections.
Are there additional questions? We still have some time. If not, I have one. In your perspective, who will find the first Earth at
the first Earth? Well,
300 orbital period, 300 days
300
in
day
period.
orbital period.
Radial velocity or transit?
Radial velocities, yeah.
Radial velocity, probably. All right. So if there are no more questions, sorry, one more. Yes, please.
I just raised the ire.
Hi, I'm over here.
Okay, sorry.
Nicole Cabrera, GSU and EPEG. I have a kind of a silly question. I actually don't know a lot about microlensing, and I was wondering if you could comment on the reproducibility, because I know it's an important method, but how do we know that these things, they're actually real detections?
Yeah. So this is actually a view that I've taken for a long time, and my microlensing friends always make fun of me when they give their talks and have some quote that I made in 1999 or something about, wait, these are planets around stars that you can't even see, that you're never going to be able to follow up on. So I think the value of the microlensing is not entirely unlike the value of the Kepler mission, where it gives us statistics about the cold planets. So I'm pretty convinced that we'll get some interesting information that way. It's not going to give us the thing some of us care about, which are the Earths and the habitable zones necessarily, and it's going to be extremely difficult to follow up on them, like some of the stars in the Kepler field as well.
Okay,
so,
thank you.
Yeah.
Pierre Bastien, I want to report the work of my colleagues. It's from Kepler data on a white dwarf, and they analyzed the data to find the pulsation periods, but there were some peaks that did not fit, and after trying out possible explanations, they had to conclude that it was due to planets.
Right.
And they are the lowest mass planets found so far.
Right.
And the most important point, I think, is that it shows that planets can survive the AGB stage during the stellar evolution.
I mean, can I ask a question, which is, do they survive, or like around the neutron star, are they reforming in an accretion disk, or whatever it is? It's incredibly exciting and cool. Yeah.
We don't know.
Yeah. Okay.
All right. So if there are no more questions, let's thank Debra again.